abstract algebra, which then you combine with general topology to do algebraic topology, applying algebraic techniques like group theory and ring theory and modules and so forth. If you don't know what I'm talking about, don't worry. Well, you probably know what groups are. And then you wed those techniques, those algebraic techniques, with topology, and you get algebraic topology. And you use those techniques from algebraic topology in higher level topology, homology, cohomology and so on, which is like M2 level algebraic topology, and you use that in turn for even higher level analysis of world sheets, world tubes. I think it's world sheets actually, technical term, for string theory. Okay, so a lot of preparation. You really have a lot of work ahead of you if you really want to understand highest levels modern mathematical physics. There's a huge amount of math prerequisite tools that you need. But if I live long enough and I'm persistent enough and I just keep doing this, because God, it's relentless, right? I think it pays to be an older person. You tend to be more on the rails. You stick on the rails more than a much younger person who's so distracted by other things. All right, now a little bit more in detail. I think the topology and differential geometry, I can say a bit more about the differential geometry, and then I'll get back to the complex variables. Differential geometry, what's that about? Largely Gauss, probably the greatest mathematician who's ever lived, German, lived early 1800s. He's pretty much the father of differential geometry. So you're applying calculus to shapes, like if you're talking curves, then there are all kinds of calculus type formulas that talk about how curves bend and twist and their curvature, how much they bend, that sort of thing. There's calculus for that. Now you do something similar for surfaces. How curvy, how is a surface, the curvature of a surface. There are famous formula, like there are different kinds of surfaces. You might like to have the surface of a sphere, which has positive curvature. You might have the curvature of a saddle, like on a horse, like it bends down this way, so your legs go down this way, but it also bends this way in another direction to keep you on the horse, right? You move forward, the saddle will push you back. You move back, the saddle will push you forward, so you stay in the saddle, right? So it's sort of like that way when the horse is moving in that direction, and it's this way. So you can put your legs either side of the saddle. So that's that kind of surface has a negative curvature, stuff like this. There are famous theorems, Gauss's theorem, that you can have a maximum minimum. Like you take a cross section through this surface, and you'll get the cross section will give you a curve. You cut your saddle with a cross section this way and that way, this way and that way, and you'll get a line. The cross section will give you a line this way, and if you cut it that way, you can't see it, but you get like a parabola, let's say this way, and a parabola that way, and the product of the maximum curvature in one cross section times the maximum curvature the other way, they're actually at 90 degrees to each other. It's a famous theorem in differential geometry by Gauss, and that level, probably pretty well the master's level, you'd study, and this is the text I'll be using. It's in the Schaum series. The author is Lipschutz, and now this is differential geometry in 3 dimensions, ordinary space, and then later we'll take it to four dimensionals. We'll bring in time, and so you'll talk about space-time, and we can have it curved, not flat. And so you're talking curved, four-dimensional surfaces, space-time, and that's the mathematics of general relativity. Right? So we'll do general relativity. We'll do tensor calculus. They're closely linked with multi-dimensional differential geometry. Okay. Now, complex variables. Why study that? Well, lots of reasons. Let me just give you a few directly relevant to higher level math physics. You need to know the calculus of complex functions, complex numbers, to solve rather complex integrals that keep popping up in quantum field theory, QFT. So it's a useful tool for QFT. You need to understand complex functions to understand something called Riemann surfaces. I won't bother explaining what they are. You can sort of guess. The genius Riemann, one of the top mathematicians of the 19th century, also German, deeply impressed Gauss. Gauss was amazed by this young guy, because Gauss was a lot older, of course. So Riemann surfaces need complex analysis to understand them. I'll be giving two courses, M1 and M2 level, on Riemann surfaces. And why? Because Riemann surfaces feature strongly in string theory. A lot of branches of mathematics feature strongly in string theory, right? It's beautiful mathematics, and even if string theory is all dead wrong, which I very much doubt, simply because it's too beautiful to be wrong, right? The mathematics of string theory is so powerful and so beautiful, there's those two words again, power and beauty, that just the impact that string theory has had on mathematics, right, is enormous. So pure mathematicians are learning string theory to understand its impact on mathematics. Low-dimensional topology has been revolutionized by string theory. Ed Witten, one of the major theorists in string theory, reputed to be one of, at least, well, it's debatable, but in the top handful of the smartest men in the world. If you ask me to choose a few others, Witten in turn was strongly influenced by the intuition and mathematical ability of a guy called Britt, I think, Atiyah, A-T-I-Y-A-H. He would be another candidate for me, one of the smartest guys in the world. If the general population hasn't a clue, right? What do the smartest guys do? Well, one of the things they do is pure mathematics, and nowadays math physics or mathics. It has such a scope for people with these top minds, with IQs over 200, literally. People like Roger Penrose, he's reputed to have IQ over 210. So these super genius minds, what do? How do they spend their time? Well, they amuse themselves with pure math and math physics. A lot of them. I'm not saying that's all they do. Some genii go into other fields. I know economics, or business, or government, or political philosophy. Marx was a genius. I don't think he was a mathematical genius, but when you have ideas that end up influencing governments such that half the populations in the world a few decades back were living in regimes modelled on Marx's ideas, you're talking a genius, right? Just by sheer influence. Well, the greatest mathics genii of the world, who are explaining, we hope, the nature of the universe, the nature of nature, and hence in time will have huge economic spin-offs, because fundamental science, the historical record shows over several centuries now of modern science, fundamental science leads to a growing understanding and hence a mastery of nature, and hence technologies. And with technologies comes usually better lives, richer lives. So these guys are, these genii are revolutionizing our whole lifestyles through indirectly through their understanding of how nature works, the nature of nature. Okay, so they are the guys creating the theories that I would like, if I live long enough and can stick with it long enough, to teach you guys what they are doing. String theory and modern mathematics, and the many branches of mathematics that are used in string theory, and particle physics, and Lie theory, and topology, and differential geometry, and so forth, and so on, and so forth. Okay. I'll stop there. I've been rambling on for ages. Ciao.